These are your notes for Unit 11, Day 3 of Pre-Calculus. If you would like to see your warm-up, review question, or any homework questions we covered in class today, just look at the finished notes. So today we are going to continue talking about matrices. We're going to be able to find the determinant of a 2x2 and 3x3 matrix. We will be able to use Cramers rule to solve a system of equation using matrices. We will be able to add, subtract, multiply matrices, and we will be able to find the inverse of a matrix and use the inverse of a matrix to find the solution to a system of equations. So the determinant of a 2x2 matrix. So we call the determinant capital D, and to find the determinant of a 2x2 matrix, what you do is you multiply across the first diagonal. So we're going to take 3 times 1, so D is going to be 3 times 1, and then you subtract, and then you take the product of the second diagonal. So 6 times negative 2 is going to be negative 12. Well, let's write that up. 6 times negative 2 would be negative 12. So I have 3 plus 12. So the determinant of this matrix would be 15. Or if we took another matrix, let's say it was 5, negative 3, 6, 4, and we wanted to find the determinant of this matrix, the determinant would be multiply the first diagonal, 5 times 4, and then subtract, multiply the second diagonal, 6 times negative 3, so this would be 20 plus 18. So the determinant of that 2x2 matrix would be 38. So how can we use determinants to find the solution to a system of equations that is a 2x2 system? Well, first, let's write this in matrix form. So this would be 3, negative 2, 6, 1. And then if I multiplied that by x times y, I would get the solution 4, 13. And so that would be my system of equation in matrix form. So what you're going to do is you're going to take the determinant of the coefficient matrix. So I'll take the determinant of this matrix. So the determinant is going to be 3 times 1 minus 6 times negative 2. So it'll be 3 plus 12. So the determinant of this matrix is 15. And then what you do is remember that this was the x column and this is the y column from before. We're going to replace the x column with the solution column. So now if I took that x column and I replaced it with the solution column, I would get 4, 13, and then the y column stays the same, negative 2, 1. And then I find the determinant of that new matrix, and we call that new determinant dx, or d sub x. And so the determinant of this matrix would be 4 times 1 minus 13 times negative 2, which would be 4 plus 26, which is 30. And then we're going to do the same thing, but this time we're going to replace the y column. We're going to replace the y column with the solution column. So then we're going to take a new matrix. And so this new matrix, the x column stays the same, 3, 6, and then my y column is going to become the solution column, 4, 13. And then we find the determinant of that matrix, and we call that determinant d sub y, or dy. And so 3 times 13 minus 4 times 6, and so I would get 39 minus 24, which is 15. So d sub y is going to be 15. Now, the solutions to my matrix, the x coordinate for my solution is going to be d sub x over d. And so in this case, it would be d sub x was 30. So it'll be 30 over d was 15. So the x solution to my system of equation is going to be 2. And then my y solution is going to be d sub y over d, which would be 15 over 15, which is 1. So the solution to this matrix using Cramer's rule is going to be 2, 1. And if I wanted to find the solution to this matrix just using our substitution or elimination methods, I could take the second equation and multiply everybody by 2. And that would become 12x plus 2y equals 26. And then I would add, so I would get 15x equals 30. And so x would be equal to 2. Substitute that back in, and you would get y is equal to 1, which is the same solution we got using Cramer's rule. So again, to use Cramer's rule to solve a system of equations, you find the determinant of the original coefficient matrix, and then you replace the x column with the solution column and find the determinant of that matrix, which we call d sub x. and then you take the original coefficient matrix and you replace the y column with the solution column, and you find the determinant of that new matrix, and that's going to be d sub y. And then in Cramer's rule, the x-coordinate solution to your system is going to be dx over d, and the y-coordinate solution will be dy over d. All right, so how do we find the determinant if it's a 3 by 3 matrix? So this is a little bit more involved. What you do is you rewrite the matrix, so 3, 4, 8, 0, 6, negative 2, negative 4, 2, 3, and then you take the first column and tack it onto the end. So I'm going to tack that column on the end, 3, 4, 8, and then you take the second column and then tack that onto the end. So that is going to be 0, 6, negative 2. And then what you do is you take all the diagonals running from left to right and you multiply those terms. So I'm going to multiply all of those and then I'm going to add them together. So add and add. So I'm going to take 3 times 6 times 3 plus 0 times 2 times 8 plus negative 4 times negative 2. And so I would get 54 plus 0, and then 8 times 4, so plus 32. And then you take the diagonals going from right to left and multiply them. So this diagonal, and this diagonal, and this time you subtract in between. And so this is going to become minus 0 times 4 times 3. And then minus 3 times 2 times negative 2, and minus negative 4 times 6 times 8. And so this would be minus 0, and then plus 12, and then plus 48 times 4, just, whoops. So 48 times 4, 192. And so the determinant of this matrix is going to be, add all those terms together, so 54 plus 32 plus 12 plus 192. And the determinant of that 3 by 3 matrix is going to be 290. So again, to find the determinant of a 3 by 3 matrix, start by rewriting the matrix. So 3, 0, negative 4, 4, 6, 2, 8, negative 2, 3. And then tack on the first column to the end, so 3, 4, 8. And then tack on the middle column to the end, 0, 6, negative 2. And then multiply across the diagonals, so 3 times 6 times 3, plus 0 times 2 times 8, plus negative 4 times negative 2. And then multiply going the other direction, so from right to left, so 0 times 4 times 3, then minus 3 times 2 times negative 2, then minus negative 4 times 6 times 8. And then simplify that expression, and that would be the determinant of your 3 by 3 matrix. So if we want to use Cramer's rule to find the solution of a system of equations in 3 variables, it's very similar to how we did it in 2 variables, but we're going to have to find the determinant of a 3 by 3 matrix several times. So let's start by making the coefficient matrix. So we have 2, 1, negative 1, negative 1, 2, 4, and 1, negative 2, negative 3. So that's my original coefficient matrix. So if I wanted to find the determinant of this, we would rewrite it 2, 1, negative 1, negative 1, 2, 4, 1, negative 2, negative 3, and then tack on the first column, so 2, negative 1, 1, then tack on the second column, 1, 2, negative 2, and then multiply across the diagonals. And so going from left to right, we would get 2 times negative 3, so negative 12, and then plus 1 times 1 is 4, then plus negative 1 times negative 1 is 1, times negative 2 is negative 2. And then we would multiply the diagonals going the opposite directions. And this time we subtract, so then it would be minus 3, and then minus 8 times 2, so it'll become plus 16, and then minus negative 2, so plus 2. And so the determinant of that 3 by 3 matrix would be -8, -10, -13, +3, +5. So the overall determinant of that 3 by 3 matrix would be +5. And now we're going to take the answer column, 3, -3, 4, and we're going to replace it. We'll start with the x column. So my new matrix would be 3, -3, 4, 1, 2, -2, -1, 4, -3, and then rewrite the first column. So 3, -3, 4, and then rewrite your second column, 1, 2, -2, and then we're going to find the determinant of that new matrix. So multiply across the diagonals. And so this would become -18 plus 16, and then plus -6, and then multiply across the diagonals going the other direction. And we would get 9, so -9, and we would get plus 24, and we would get plus 8. And so the determinant of that 3 by 3 matrix would be -17, 15. So we would get -2, -8, -17, +7, yep, so 15. And now we're going to take the y column of the original coefficient matrix and replace it with the solution column. So I'll have 2, -1, 1, and then the y column becomes 3, -3, 4, and then we still have -1, 4, -3, and then repeat the first column, so 2, -1, 1, and then repeat the second column, 3, -3, 4, and then we're going to call that new determinant dy. So multiply across the diagonals, and we would get +18, +12, +4, and then multiply across the diagonals going the other direction, and we would get -9, and then -32, and then -3. And so if I combine the like terms, I would get 34, and then 2, and then -7, -3, so that would be -10. So my determinant dy would be -10. And then we've got to find our dz. So now I'm going to replace that last column with my solution column. So I'll replace the z column with my solution column. So I would have 2, -1, 1, 1, 2, -2, and then my z column becomes 3, -3, 4. Then repeat the first column, 2, -1, 1. Repeat the second column, 1, 2, -2. And then find my determinant. So multiply across those diagonals. And I would get dz equals 2 times 2 times 4 would be 16. And then we would get -3, and then we would get +6. And then multiply across the diagonals going in the other direction. And this time you subtract. So it would become +4, and then -12, and then -6. And so dz would be 13, 19, 23, 11, 5. All right, so now you have all of your determinants. And so the x coordinate to the solution to the system of equations would be dx over d, which would be 15 over 5, so it would be 3. The y coordinate solution would be dy over d, so it would be -10 over 5, so -2. And the z coordinate solution would be dz over d, which would be 5 over 5, which is 1. So the solution to this system would be 3, -2, 1. And you can always check your answer by plugging it back into all 3 equations and make sure it works. So 6 minus 2 minus 1 is 3. So it works in the first equation. So again, using Cramers rule on a 3 by 3 system is kind of tedious. You can also solve the system algebraically like we did earlier in the chapter, but this is how you would solve it using Cramers rule. All right, how to add and subtract matrices. In order to add or subtract matrices, they need to have the same dimensions. And so they need to have the same rows by columns. If they don't have the same dimensions, you can't add or subtract them, because what you do is you just add the elements in the same position. So matrix A plus B is going to be, well, you would take the element in the first column, first row, and add it to the element in the first row, first column of the second matrix. So that would be -1. And then you would take the second element and add it to the second element. So it would be 8, and then so on and so forth. So you would get 8. You would get -2. And then in the second row, you would get 6, 9, 4, and 3. And so that would be matrix A plus matrix B. If you wanted to do matrix A minus matrix B, you do the same thing, but this time you would subtract. So 2 minus -3 is 5. 4 minus 4 is 0. 8 minus 0 is 8. -3 minus 1 is -4. 0 minus 6 is -6. 1 minus 8 is -7. 2 minus 2 is 0. And 3 minus 0 is 3. And so that would be your answer to matrix A minus matrix B. All right, scalar multiples of a matrix, you just multiply every entry in the matrix by the scalar multiple. So 4 times matrix A, you would just multiply every element by 4. So this would be 12, 4, 20, -8, 0, 24. And that would be 4 times matrix A. If you would wanted to do 1/3 times matrix C, you would just multiply every element in matrix C by 1/3. So 3, 0, -1, 2. For C, we want to do 3 times matrix A minus 2 times matrix B. So let's do 3 times matrix A first. So that would be 9, 3, 15, -6, 0, 18. And then we want to subtract 2 times matrix B. So let's do 2 times matrix B. That would be 8, 2, 0, 16, 2, -6, and then subtract them. So 9 minus 8 is 1, 3 minus 2 is 1, 15 minus 0 is 15. -6 minus 16 is -22. 0 minus 2 is -2. 18 minus -6 is going to be 24. And so that would be 3 times matrix A minus 2 times matrix B. Matrix multiplication is a little bit more of a tedious process. So if you want to find the product of matrix A times matrix B, what you do is you take the first row of matrix A and you multiply it by the first column of matrix B, and that's going to give you your first entry. So you multiply all of the terms and then add up the products. So we're going to do 2 times 2 plus 4 times 4 plus -1 times -3. So again, we did the 2 times the 2, the 4 times the 4, and then the -1 times the -3. And that's going to give you just the first entry in your product matrix. Then what you're going to do is you're going to do the same thing, but then you're going to take the first row of matrix A and multiply it by the second column of matrix B. So we're going to do 2 times 5 plus 4 times 8 plus -1 times 1. So again, we take 2 times 5, 4 times 8, -1 times 1, and add up all of those elements. And then you're going to do the same thing, but you're going to do it with the third column of matrix B. So we're going to take 2 times 1 plus 4 times 0 plus -1 times -2. So again, 2 times 1, 4 times 0, -1 times -2, and add all those entries. And then you're going to do the exact same thing, but with the last column. So notice this will only work if the number of entries of the rows in matrix A is the same as the number of entries in the columns of matrix B. So we're going to take 2 times 4 plus 4 times 6 plus -1 times -1. And that is going to give me the first row in my product matrix. So again, we took 2 times 4, 4 times 6, and -1 times -1. All right, so then what we're going to do is we're going to do the exact same thing, except for this time we're going to use the second row in matrix A and multiply it by every column in matrix B. So we're going to do 5 times 2 plus 8 times 4 plus 0 times -3. And then we're going to do it with the second column in matrix B. So 5 times 5 plus 8 times 8 plus 0 times 1. And then we'll do it with the third column in matrix B. So we're going to do 5 times 1 plus 8 times 0 plus 0 times negative 2. And then we will do it with the last column in matrix B. So 5 times 4 plus 8 times 6 plus 0 times negative 1. And now we just simplify this. So the product of matrix A times matrix B would be 4 plus 16, so 20 plus 3 is 23. And then 10 plus 32 would be 42 minus 1 is 41. And then 2 plus 0 is 2 plus 2 is 4. So we have 23, 41, 4. And then we have 8 plus 24, so 32 plus 1 would be 33. So that would be our first row in our product matrix. And then we have 10 plus 32, so 42, and then plus 0 would stay 42. And then we have 25 plus 64, so 64 and 25 make 89, and then plus 0 would be 89. Then 5 plus 0 would be 5, and then 20 plus 48 would be 68. And so that would be my product matrix, A times B. All right, let's try another one. Let's try and find A times B. So we would take the first row of matrix A and multiply it by the first column of matrix B. So A times B would be 2 plus 2 plus 9, and then do it with the second column of matrix B. So it would be 0 plus 1 plus 6, and then we will take the second row of matrix A and then multiply it by the columns of matrix B. So we would have 1 minus 2 plus 0, and then do it to your second column of matrix B. We would have 0 minus 1 plus 0. So matrix A times matrix B would be 13, 7, negative 1, negative 1. And so that looks what matrix A times matrix B would be. All right, if you wanted to do matrix B times matrix A, you would take the first row of matrix B and then multiply it by the first column of matrix A. So you would do 1 times 2 is 2, 0 times 1 is 0. So again, you would take 1 times 2 and 0 times 1. All right, then do it to your second column of matrix A. So it would be 1 plus 0, and then do it to your third column of matrix A. So you would get 3 plus 0. And then do your second row of matrix B. So 2 times 2 is 4, 1 times 1 is 1, 2 times 1 is 2, 1 times negative 1 is negative 1, 2 times 3 is 6, 1 times 0 is 0. And then do it with your third row of matrix B. So 3 times 2 is 6, 2 times 1 is 2, 3 times 1 is 3, 2 times negative 1 is negative 2, 3 times 3 is 9, 2 times 0 is 0. So matrix B times matrix A would be 2, 1, 3, 5, 1, 6, and then 8, 1, 9. And that is how you would do matrix multiplication. So why don't you guys pause the video and find A times B and B times A. You can check your work against the finished notes from class today. All right, what is the identity matrix? Well, the identity matrix we label with I. And so a 2 by 2 identity matrix would have 1s down the diagonal and 0s everywhere else. So the identity 2 by 2 matrix would be 1, 0, 0, 1. The identity 3 by 3 matrix, again, would have 1 down the diagonal and 0s everywhere else. So it would be 1, 0, 0, 0, 1, 0, and 0, 0, 1. And then that would be true for any identity matrix. So it's a square matrix. It has the same number of rows as columns. You have 1s down the diagonal and 0s everywhere else. So to find the inverse of a matrix, it has to deal with the identity. Because remember, inverses undo each other. So A matrix and another matrix are inverses of each other if their products going both directions are the identity matrix. So let's take A times the inverse of matrix A. So if we took A times the inverse of matrix A, so remember you take the row times the column. So we would have 3 minus 2, and then we would go this way, and we would have negative 3 plus 3, and then you would do the same thing but with the second row of matrix A. So you would have 2 minus 2 and negative 2 plus 3. And if you simplify that, you get 1, 0, 0, 1, which is the identity 2 by 2 matrix. But again, for an matrix and another matrix to be inverses, you have to be able to multiply them both ways. So the inverse of A times A also has to be the identity matrix. So let's multiply it the other way. So we're going to take the rows of the inverse times the columns of matrix A. So 1 times 3 is 3, negative 1 times 2 is negative 2. And then do the same thing with the second column. So you would have 1 minus 1, and then do your second row of the inverse matrix. So negative 2 times 3 is negative 6, 3 times 2 is 6, and then negative 2 times 1 is negative 2, 3 times 1 is 3. And if you multiply this out, you would get 1, 0, 0, 1, which is also the identity matrix. So since the product of A times the inverse of A and the inverse of A times A are both the identity matrix, then those two matrices are inverses of each other. That is one way to show that a matrix and another matrix are inverses. You can also find if it's a 2 by 2 matrix and you want to find the inverse, there's another relatively easy process to do this. One, you find the determinant. So if I found the determinant of matrix A was 3, 1, 2, 1. So if I found the determinant of matrix A, I would get 3 minus 2, which is 1. Then what you do is you do 1 over the determinant, and then if your original matrix was A, B, C, D, you do 1 over the determinant, you flip-flop that first diagonal, and then you make the second diagonal negative. So you flip-flop that first diagonal, so switch around the A and the D, and then you make the second diagonal negative. So the inverse of matrix A would be you take 1 over the determinant and then switch around the first diagonal, so 1 and 3, and then make the second diagonal negative. And then if you multiplied that out, you would get 1, negative 1, negative 2, 3. And notice that is exactly what we found the inverse of matrix A to be. And so that is a process. If it's a 2 by 2 matrix, that's how you can find the inverse of a 2 by 2 matrix. Find the determinant. It's 1 over the determinant. And then you take your original matrix, you flip-flop the first diagonal, and then you make your second diagonal negative. Another way to find the inverse of a matrix, and this is for a 3 by 3 matrix, is you can rewrite your matrix as an augmented form. So you rewrite your matrix and then put the identity matrix right next door. And then you're going to transform that original matrix into reduced row echelon form. And that is when you have 1s in the diagonal, 0s everywhere else. And then once you do that, you will have the identity matrix on the left and the inverse matrix will be on the right. So let's try this. This is kind of a lengthy process. So we're going to take your matrix and rewrite it. So 1, 1, 0, negative 1, 3, 4, 0, 4, 3. And then we're going to put the identity matrix next door. So 1, 0, 0, 0, 1, 0, 0, 0, 1. And what I want to do is I want to take the left side and I want to rewrite it so it's in reduced row echelon form, which means it's going to look like the identity matrix. So it'll have 1s in the diagonal, 0s everywhere else. So notice, in order to do that, we need 1 as our first entry. We have 1 in our first entry, and then we want 0s everywhere else. Well, in order to do that, I need a 0 where that negative 1 is, and so I can take row 2 plus row 1, and I would get that. So if I did row 2 plus row 1, I would get 1, 1, 0, and we would still have 1, 0, 0. And then I would have 0, 4, 4, and then 0, 1, 0. Oops, that's not true. I'm adding, so this one would have a 1 right here because 0 plus 1 is 1. And there we go. And then this row would stay the same, 0, 4, 3, 0, 0, 1. All right, so now I've got 1, 0, 0. And now I need a 1 right here. Well, to get a 1 right there, if I wanted to, I could divide everybody by 4. So I could do 1/4 of row 2, and I'd have a 1 right there. So if I did 1/4 of row 2, and then if I also did, I want a 0 right here. To get a 0 right there, I could do row 3 minus, well, I don't want to do that because I want a 0 there. I could do row 3 minus the original row 2, and I would get a 0 right there. And so my new matrix would be, we would have 1, 1, 0, and then 1, 0, 0. And then I'm going to take row 3 minus row 2. So 0, 0, negative 1, negative 1, negative 1, 1. And then I'm going to do 1/4 of row 2. So 0, 1, 1, 1/4, 1/4, 0. All right. So now I need this number right here to be positive 1. So I'm going to do negative 1 times row 3. And I would get 1, 1, 0. And then 1, 0, 0. And I would get 0, 1, 1, and 1/4, 1/4, and 0. And I'd get 0, 0, 1, 1, 1, negative 1. All right, we're almost there. But now I need these numbers right here to become zeros. And so to get those numbers to become zeros, I could do row 2 minus row 3. And if I did that, let's add a page. If I did row 2 minus row 3, I would have 1, 1, 0, 1, 0, 0. And then if I did row 2 minus row 3, I would get 0, 1, 0. And then 1/4 minus 1 would be negative 3/4. 1/4 minus 1 would be negative 3/4. 0 minus negative 1 is 1. And then I would still have 0, 0, 1, then 1, 1, negative 1. And then my last step is I need a 0 there. And so to get a 0 there, I could do row 1 minus row 2. And if I did row 1 minus row 2, I would get 1, 0, 0. And then 1 minus 3/4 would become 1 plus 3/4. And then 1 plus 3/4 would become 7/4. And then 0 minus 3/4 would be 3/4. And then 0 minus 1 is negative 1. And then everything else stays the same. So 1, 0, 0, 1, 0. Then negative 3/4, negative 3/4, 1. And then 0, 0, 1. And then 1, 1, negative 1. Now notice we are in reduced row echelon form, which is also the identity matrix is on the left. So that means that the matrix on your right side is the identity matrix, or sorry, not the identity matrix, it's the inverse matrix. So the inverse of matrix A is going to be the matrix 7/4, 3/4, negative 1, negative 3/4, negative 3/4, 1, and 1, 1, negative 1. And so that is one way to find the inverse matrix of a 3 by 3 matrix. Again, it's a lengthy process. All right. So if you wanted to use a system of equations to solve, if you wanted to use matrices to solve a system of equations, what you can do is if you took your inverse matrix and you multiplied it by what we're going to call the x matrix, you would get your solution matrix. So you would take the inverse matrix times x. So what you would do first is you would do your coefficient matrix. So 1, 1, 0, negative 1, 3, 4, times 0, 4, 3. And so that's matrix A. And then you would multiply that by x, y, and z. And we would call that matrix X. And that's going to equal your solution matrix, 3, negative 3, 2. We could actually, nope, sorry. Let's go, if you take the inverse of A times the solutions matrix, you would get your X, Y, and Z. So that would equal X. So X, Y, and Z. So that would tell you what your X, Y, and Z are. So if you take the inverse matrix times your solutions, 3, negative 3, and 2, you would get your X, Y, and Z. Now, we remember from up above how long it took us to find that inverse matrix. So that's not going to be the quickest way to solve this system. So we're actually not going to solve this system using the inverse of matrices. I believe in your digital book, there's a video of this being solved using the inverse matrices. But we're just going to solve this matrix using substitution or elimination. I can eliminate the x's in these two equations by adding. And so if I added those two equations together, I would get 4y plus 4z equals 0. And then notice my bottom equation hasn't been used yet, and that's 4y plus 3z equals 2. And if I subtracted all of those, I would get z equals negative 2. Notice that was pretty quick. So when you're going to solve a system, I would solve it using the quickest method possible. Now, if I took that and plugged it back in, I would get negative x plus 3y, then minus 8 equals negative 3, and I would have x plus y equals 3. I'm going to add the 8 to the other side, and I would get negative x plus 3y equals 5, and then I can add all of these together to eliminate the x's, and I would get 4y equals 8, so y is equal to 2. So I have y is equal to 2, z is equal to negative 2, and I know that x plus y equals 3 from that first equation. So x plus 2 equals 3, so x is going to equal 1. So the solution to this system would be 1, 2, negative 2. All right, your homework is from 11.3 and 11.4. Let me know if you have any